Okay, we will continue now and we will switch to another very important topic, which is robotics, is about building machines which cannot only understand language, but which should be able to act in the real world in order to improve quality of life of people, in order to provide meaningful jobs for people. And it's a pleasure for me to have such great panelists here, or speakers, Professor Manuela Veloso from CMU, Professor Giorgio Metta from Italian Institute of Technology, Nagin Cox from NASA GPL, and Professor Oussama Khatib from the Stanford University. So my name is Tamim Asfour. I am a friend of Alex, and at the same time, I'm professor at the Karlsruhe Institute of Technology working on humanoid robotics. And in the interest of time, we will start immediately with the first speaker, and the first speaker is Professor Oussama Khatib from the Stanford University. He is also the director of the Stanford Robotics Center. What I can say that Oussama, over the last 4 decades, he actually shaped the field at its core. So his work and research on ranging from motion planning, control to human-centered design, haptic interaction. There are only few examples of what we actually teach our students these days in every robotic course. Oussama is IEEE Fellow, member of the National Academy of Engineering, and he is behind the development of one of the exciting robotic systems for dexterous manipulation underwater, right? And I think he's going to tell us more about that in his short presentation. Oussama, please, the floor is yours. Please welcome Professor Oussama Khatib.
Thank you, Tamim. And let me first take you to a very nice place. I think Alex remembers this place, right? Alex, Captain Alex. I had the most amazing experience flying on the Grand Canyon with Alex, and how can you see the inside? I mean, always we see the outside of the Grand Canyon, but from the inside, it was amazing. Thank you, Alex. Always. So I'm here to talk about what? About Interact. Interact is actually the glue to much of the things we are all talking about today. One aspect of robotics is really the experimental work, the field work. And Ocean 1K represent one of the extreme cases of challenges you can imagine, moving in the water. But a robot like this, I mean, you have to remember, robots also has hobbies. And this robot likes to swim with race, likes to play basketball, chess, pool, and also it likes to read. So it was featured in the Scientific American, and I like this image of the robot reading the magazine remotely. And in fact, this robot was in the aquarium of Singapore just a few weeks ago, and the robot was swimming with sharks and racing race. Basically, the robot lost. So the robot is always carries your hands and eyes in the water through haptic interaction, and you're able to feel and touch what the robot is doing. Here, the robot is actually interacting with the operator, and through this motion, you can see the robot is lifting a vase that was placed by the divers, and etc. We don't have too much time, but the conclusion was amazing. The robot made it to the cover of the most important newspaper in Singapore. Now,
this record would enable archaeologists to excavate countless wrecks of warships, merchant ships, aircraft, and submarines from every era that have up until now been totally inaccessible. But how can we be sure that Ocean One will withstand the extreme pressures? Or that its bionic hands will be able to recover sunken objects from the abyss?
So this is actually a documentary film about this robot, and I hope you will have the chance to take a look. It's really, really a beautiful rendering of the expedition we had between 2021 and 22 in the Mediterranean that took us all from 40 meters all the way to 1,000 meters. And the year after the robot went to Deep Dive Dubai, Deep Dive Dubai is the deepest pool in the world, and the robot here is working. Robots needs also to have fun. So here the robot is playing, not only playing, but winning, of course. Just a short video showing, these are my students about to dive with the robot. The stereo images are shown in double image, as you can see on the screen. Working. Checkmate. Underwater. So this is the main point. Human-robot interaction. And it is really, really amazing that we just talk about autonomy, forgetting the interface between the human and the machine. And this is not only for underwater or for space. Here is many examples. This is an example of ultrasound scanning done by introducing the haptic interface, and now we are able to see the image, and now we are able to separate the patient from the doctor, radiologist, and now we can reach beyond where hospitals are. We can go to areas that are rural without hospital access, and we can deploy mobile clinics to connect hospitals to those places. This is actually a project in Thailand, and the Princess of Thailand here was looking at this project where I was controlling a robot at Stanford from Bangkok, and remotely I was able to identify the 3 dark areas where we have high density tissues, telling us there is a major problem with this patient. Now, the idea is really to make a network, another network, Alex, we need to do to connect the world where we have no access to medical care. So essentially, the internet that allowed us to hear and see is now allowing us to touch and feel. This is the physical interact. And I really believe we are now able to do it because of convergence of technologies in communication, in material, in robotics, in AI, in many aspects of the work. So what is robotics? Sometimes we simplify robotics to just a connection between one image and action. Robotics has a lot of requirement for the knowledge, understanding of the robot systems, about the design, about the interaction, about what application and what interaction tools we are going to develop. We need to think about the physical robot. We reach a milestone with robots that has integrated torque sensing and capabilities. Now we are going to the future with newer robots that are for us who are working with robots, dream robots. And this is Maestro, just a new robot about 10 days ago, came out with 2 of my student graduating at Stanford. It is a wonderful machine. We don't have time to talk about it, but the software platform is another important thing. The software platform is a place where you simulate, control, and test your concepts. The architecture of control. Architecture of control is a multi-layer system, and this is what enabling us to get autonomy, but I call it functional autonomy because the cognitive autonomy is still require the human interface, and this is how we can really achieve real work and results. Finally, the robot, here is our boat. The robot is controlled and carrying the capability of the human. And these are some of the artifacts that we brought from a Roman boat, 2,000-year Roman boat left to the east of Corsica, oil lamps and pieces of wood from that boat. And then we went down to the Crispy at 500 meters. And then finally we reached 1,000 meters at Cannes, where the robot was diving all the way. And I leave you with this short video showing a little bit of the interaction with the physical environment and how we are able to touch and feel what we are doing and how we place all these objects that we recover and then bring them back to the surface. So this is these are some of the objects that you are seeing here, 2,000-year-old, and you can imagine how happy the archaeologists were to see these artifacts coming from the past, and they studied without. So here we discover with the marine biologist the area where we have iron-eating bacteria, which will eat the whole boat, essentially, after centuries. And we think wooden boat are more fragile. Actually, the ones that are most fragile is the metal boats. Here, finally, we are reaching the depth of, amazing depth of 852 meters, and we touch the ground. 1,000 meters is equivalent to 100 times atmospheric pressure, and this is quite amazing performance for a robot that is capable of doing dexterous manipulation and bringing things really safely to the surface. Well, this is the future, Alex, and thank you so much for this amazing opportunity to meet all our friends and to celebrate you. Alex, thank you so much.
Yeah, thank you very much, Oussama, for the wonderful presentation. We'll move to the next speaker. So Nagin Cox is a systems engineer at NASA JPL. She worked on some of the most exciting missions of our time, space missions of our time, from the Galileo mission to Jupiter, to the Mars rover Curiosity and the Europa Clipper mission. She has several awards. Maybe the most exciting award for me is that today an asteroid bears her name, this asteroid 14061. Please join me in giving a warm welcome to Nagin Cox. Please.
Guten Tag. That's all I know. My name is Nagin Cox. Thank you, Alex, for the invite to be here. So continuing the theme of human and robotic interaction, we will talk just a little bit today about how robots help us explore space and have been doing so for many years. I've been working in robotic space exploration for over 30 years and with a focus on Jupiter and Mars missions. And I am currently a mission lead on the Perseverance rover that landed on Mars in February of 2021. So most of us are probably familiar with these two pictures, the 1968 Apollo 8 Earthrise image that was taken by the astronauts in lunar orbit. And then very recently, just in the last couple of months, the Earth set image from the Artemis 2 mission as the astronauts flew by over the dark side of the moon. So in between those two photos, we landed on the moon. We learned to go into space reusably by using the space shuttle, and we learned to live in Earth orbit. We have had humans living on the International Space Station for the last 25 years. While that was happening, we have also been exploring space robotically. Before we send people, we send robots, and the robots have been all over the solar system. So I work in mission control, like you've seen in the movies, and if you are watching the Artemis 2 broadcast, only the difference is that my team talks to a rover on Mars instead of talking to an astronaut like the Artemis mission control area does. So we design, we build, we launch these spacecraft, we fly them to their destinations, and then they begin to answer the questions that we have posed for them. We have had rovers on Mars since the late 1990s. I've worked on 4 of the rovers. Spirit and Opi were my first 2 rovers, and Curiosity, and now Perseverance. These rovers and these robotic vehicles and spacecraft, they carry suites of instruments. They carry instruments designed to answer the questions that we have posed for them. We ask them to answer questions of exploration as well as questions of science. We prepare for human exploration while also trying to answer big questions like, was there ever once life on Mars in the distant past? These robots are our partners. They are our emissaries. They go before we can. So they find out what a world is like. They are our eyes, our ears, and we get attached to them, as I can attest to how attached our teams become to our rovers. We are not able to joystick these spacecraft. They are too far away. The one-way light time from here to Mars can be as much as 20 minutes. So we communicate with them by sending a series of commands, not joysticking them. So Percy will wake up at about 9:30 in the Martian morning. We send her a series of commands through big antennas that are located around the world, and then she will carry out her program for the day without any further interaction from the Earth. So she will execute that sequence of commands, and then at the end of in the Martian afternoon, we'll send the data back to the Earth that we will then interpret through the telemetry and the software that the rover has. It is still about the people, even though we're talking about robots. As I have been doing this for 30 years, we have gradually started adding more and more automation and autonomy to these rovers. So we still get the data about what happened on the prior the Martian day on Mars, and then make decisions about what we will do next. Over time, the rover, because it's on Mars, we've given it the capability to decide for itself more of what to do. But as we've heard in other discussions today, it's still about the people making the decisions. The autonomy on the rover is not replacing the humans that are controlling it. It is that we shift our focus to getting more done, and what if something goes wrong? But you still have to train the people. We talk about training the large language models. We talk about training the AI. You also have to train the people to change how we do decision-making, to give different decision-making to the rovers so that they can do things like land more precisely, use the increased CPU capability that we have been able to add to these missions over the years to land more precisely, to drive further on Mars, to decide where to drive and where to sample in some of these decade-long missions that we fly, to decide where to target. We are used to picking at the end of a drive what we're going to sample or what we're going to look at. And now we've had to learn, what do we do when we're telling the rover, go to this location, and then decide for yourself what target to pick? How do you translate what the scientists will want into instructions that the rover will understand so that it picks the same target that the scientists might have been interested in? Being able to add autonomy to the rover so that it can look ahead and see what the obstacles are, so that it can ingest images from orbit and see what the terrain is like ahead of it, so that it can make decisions about where to go as it's driving. This means that we can drive further and further with every Mars rover that we've sent. And now as we're looking at long-distance rovers on the moon, applying that same learned technology of how do we go further and do more. We have rovers, we have orbiting spacecraft, and now, Alex, we have helicopters that are on Mars. So we did our first Ingenuity Mars helicopter flight in April of 2021, and we thought we would be successful if we did one flight, and we actually did 72. So we have now learned how to fly a small drone on another planet. We've added another level of exploration capability. But again, this heli can fly itself and figure out by looking at the ground, what are the dangers, where should it land, how far should it go? So as we add these capabilities, we can do more. I have been very privileged to be a first-generation Martian. We live on the Earth, but we work remotely on Mars, and I've been working remotely on Mars continuously for over 15 years. We paved the way for humans to take the next steps. This is about technology in the service of humanity. Our robots go before people, but everything we're doing is in the service of the whole planet. When I started out in this business, this slide looked very different. Now there are so many space agencies, so many commercial companies, so many universities involved. So as we talk about the ability that partnering with robots gives us to explore space, what is really the most important is that as humans, we go and we go together. Thank you.
Yeah, thank you very much. Partnering with robots. You see, robots actually are crucial and important for the future of humanity. Yeah? And if you put them together in connection with language and speech technologies, then I think we have the perfect solutions for the future of the planet and of the society. So our next speaker is Giorgio Metta. Giorgio is today here as the scientific director of the Italian Institute of Technology. He is a researcher on cognitive robotics. He did a PhD in Genoa and a postdoc at the MIT AI Lab and was professor at the Plymouth University on professor for cognitive robotics at the Plymouth University before he took over the scientific direction or the scientific director position of IIT. In the robotic community, he's best known as the person behind the iCub robot, a child-sized humanoid robot, which he really made as the de facto reference platform for embedded AI research. The platform is distributed more than 50 platforms in Europe, in Asia, and in America. And we are happy to have you here, Giorgio, and looking forward to your presentation. Please welcome Giorgio Metta.
So, thank you, Alex, for the invitation. It's a pleasure. I was trying to remember when we met the first time, and I think besides some sporadic encounters in Karlsruhe, there was one meeting that I remember very well. I think it was in LA, and it was an interactive meeting. You invited us, delegation. There was me, Giulio Sandini. I remember Rudiger being there, Tamim. It was an incredible meeting. I think this one is better though. So you managed to improve on that experience. And the other thing I remember is the picture of the Grand Canyon. I think I was there. Oussama came back from the flight and was telling us how amazing it was. Again, it was another conference with the same, known suspects. Tamim was there. So thank you for, not forgetting to invite me again. I'm very happy. Happy birthday, by the way. So let me tell you, I never work on language. So I had a problem today trying to figure out what to say. So I went through my slides and I started thinking about maybe the human-robot interaction. That is something that we're doing, still using the ICAP after 20. So the project was born in 2004. So supposedly the little child is now 22 years old, and you can feel the difference with the modern robots. Technology, luckily, has changed quite a lot. But anyway, I wanted to discuss this with a twist. Because I heard about translation earlier, beautiful presentations. I was super happy to see all this stuff that is happening, but I thought maybe there's something that us, roboticists, can still bring to the discourse, which is about embodiment. And especially a piece of work, I didn't have to search too far because this is a work of my wife, so kind of easy. We keep the stuff at home, in a sense. She also works on the ICAP. And it's about sense of agency. So she's a cognitive neuroscientist, so you can see where the research is going. The sense of agency, is the feeling that we all have when we do something to understand that what happens is because we've done something. So I press the button, lights goes on, or computers goes off, whatever. But we have this connection with our actions and with our body. Why bother? Well, because you can be doing joint action with robots. You can be doing teleoperation, very concrete application, and also for prosthetics. Have you ever thought of all the prosthetic users are very tired by the fact that there's no feedback, there's no understanding, or there's no feeling of being in control of what the prosthetic device does. Therefore, what we've done specifically at IIT, we use cognitive neuroscience methods to try to measure what it means, in fact, to be in control. There are two measures. Without entering too much into the details, this becomes technical, but there's a way. Basically, if you press a button and you hear or you see the light coming on, or press the button and there's a sound and there's a delay between the two events because it's computer controlled, you can be asked to estimate what the time was between the two events. And you typically, if you're in control, you underestimate. If you passively moved, like your finger is moved by someone else touching the button, you estimate a longer time between the two events. So there's a way to check what is your feeling with respect to control. There's also a way through EEG, it's called sensory attenuation. It's another method that's kind of equivalent, but it's a confirmation. If you run the two, you can have better data. And there's something with the robots that is interesting, is the sense of joint agency. So what happens if I'm doing something with a robot? Can I maybe feel or being in control of the robot, but not because I'm moving it like in teleoperation, but because the robot is collaborating with me, is working with me, we're working together. We may be communicating something while developing the task together. We put together a little experiment, which is about the sense of joint agency indeed. It's a simple game. You press a button, you move a cursor on a screen, you reach a target, and you confirm with another button. So simple enough. You can play with the robot. The robot can either be moving the cursor or just confirming. And of course, this leads to 3 different cases. You can do with a person, you can do with a robot, and we wanted to see whether there are differences. This is the game. You see a robot pressing the button, and you confirming that the target was reached, and then you ask to judge how much time has passed. There's a sound here. I cannot show the sound, but there's a sound which is, again, the 2 event difference in time that you're going to measure on a scale. This is the hypothesis. So if there's a sense of joint agency, whatever you do, you always feel in control. If you're playing alone, of course, if you're the one moving the cursor, if you feel like collaborating with a robot, we expect to be seeing no difference. And if you're the detector, the guy that is pressing the final button, of course you're in control because you press, and after a certain time, there's a sound. So you're the one generating the sound. On the other hand, with a robot, you may not be in such intimate relationship, and therefore, when you're moving, you don't feel like you're in control of the robot. If that's a situation, there's a difference in timing. So we ran the experiment, but we wanted also to do a bit of manipulation. Wanted to kind of convince you that the robot is indeed like a human. We did through a session that is shown here, where you interacting with the robot does silly things like laughing at a video. There are National Geographic videos, and the robot laughs, does a whole bunch of things. It talks to you. It tells you, oh, what's your name? It does a bit of interaction. And what happens is that this is another case that we can try, whether we do this first or we don't. So whether you think the robot is a robot or the robot is not a robot, because indeed has interaction capacity that is like human. So human to human, flat, no differences. You take the ICAB, you put it there. Unfortunately, the robot stays as a robot. But if you watch the videos together with the robot, the National Geographic videos, or the pink flamingos, for instance, then something changes and it's flat again. So the robot can become intentional. So it's something that is indeed collaborating with you. So there's through this watching videos together, we've been able to manipulate your perception of the robot, and you feel like really collaborating with the robot. And isn't this communication in robotics form? Question mark. Thank you.
Yeah, thank you very much, Giorgio. We will move to our next speaker, Professor Manuela Veloso. So Manuela is Herbert Simon University Professor Emerita at CMU, where she led also the machine learning department. She is also the co-founder of RoboCup. This is the international robot soccer competition, and where her teams, she's not only the founder, but her teams actually have been several times world champions. At CMU, her cobot robots, the famous cobot robots, they navigated more than 1,000 kilometers in university buildings. This is also a record. I'm not aware of any robot developed actually in research which was able to navigate 1,000 kilometers in a building or in several buildings. And with that, she pioneered what she called symbiotic autonomy. The idea of building an AI which knows when to ask a human for help. So in addition to that, in the last 8 years, actually, she founded and led the AI research at JP Morgan Case, and she was also a past president of the AAAI, and member of the National Academy of Science and fellow of IEEE, IAAI, and ACM. Please welcome with me Professor Manuela Veloso.
Thank you very much. So I'm going to tell you a little bit, three things very simple. But these have to do with the fact that I've been involved with doing the autonomous robots as teams. So I'll explain this. So first of all, I was there in 1990 at Carnegie Mellon with Alan Newell when he actually wrote on the board these three words, perception, cognition, and action. and literally kind of like said that this science of AI needed to be integrated with these capabilities of language, sensing, and reasoning, and actually acting. So this is not a picture. We didn't have iPhones, but this is how I remember on the blackboard of 5409. I'm sure Alex and all the other CMUers know 5409. So this is what I made my life at. So I literally decided that I was going to do this perception, cognition, and action for the rest of my life. So I built tons of robots, worked with robots, always trying to close this loop of autonomously combining perception with reasoning and with action. So I'm just going to focus on this problem, given that we are here for Alex and so much language and so much communication, this problem of communication. So I'm going to go through you the following example. So we have these robots at some point that had a camera. So they have at the tip of their nose a little camera, and they also could eventually communicate with each other. So the problem becomes, oops, what do they see? And, oh, I see. Oh, this video. Does it work? No. Oh, well, sorry. Doesn't work. Can you click on some kind of the video? So the reason why it's oh, there you go. It's just, oh, it says something. Okay, it doesn't matter. What matters is that this is what they see, and it gives you a good understanding if you see this moving, that they lose what they see because they have a single sensor at the tip of their nose, and as they move, the images all tilts and everything. Anyway, this video, which we are not able to show, I guess, is the one most downloaded from the Carnegie Mellon Robot Soccer website, because it shows how difficult perception is when a machine with 4 legs is moving. But let's go on and then we'll see it later. So basically what I want to tell is like this. If they are talking with each other, and think about this, you need to find a common language. So it cannot just be with respect to yourself. So the robots, to share information among them, have to basically find this common understanding. And the one that receives the information, or when they communicate, they have this challenge. How do they combine what they see with what the others are telling? I mean, you read the New York Times, you read the Wall Street Journal, you read the Le Monde, you read everything, and now you have to yourself build your own beliefs. So I'm going to show you this because this is like a robot kicking the ball into the goal. And it doesn't matter whether it's soccer or less soccer. It's an agent that perceives where the ball is and needs to achieve a task, which happens to be and I'm showing it again. And the reason why I'm showing it again, because there is a detail here. When it kicks the ball, it does not see the ball. It actually, the camera is in the chin and the ball is in the chest. So does the whole action in open loop. And then it eventually, so that I'm going to show you one more time, because look where it looks after the actual, let's see, not this one. We'll see. But here, it's actually here we are going to steal the ball and give the ball to another teammate. And by the time the teammate says, they are communicating, and that one finally believes on what the other doing, and is doing all this motion without seeing itself the ball until it eventually sees. So this is, and whether it's fun or not, I mean, ignore the soccer, ignore this thing, but what I'm telling you is like this. Look at this mystery of having agents talk with other agents. And this mystery of someone telling me something has happened, I don't know where, and I have to act based not on my sensing, but on what I was told. So you need to, if you see, just see how now finally it so it doesn't believe it's there, it keeps searching around it, finally it believes that's back there, but this walk is all not seeing it itself. Do you understand how beautiful this is from an agent point of view? because they act based on what the other's saying. So we invented this kind of little algorithm that enables you to decide, you a robot, to decide what's the state of the world by using your own perception. But then if your own perception does not cover what you need to act upon, you basically generate a probabilistic set of hypotheses, or either I kicked it there, so maybe it's there, or someone else is telling me. And you might have many, many voices, and you might have to rank those hypotheses based on trust and go to visiting these hypotheses in order. And I tell you, the worst you don't want to do is average what everybody is telling you. Because if you average what everybody is telling you, you definitely are going to a place where there is no ball. Do you understand? But so this is like the magic of multi-robot systems. So look how beautiful. This is the last video I'll show of the soccer, in which this team, the red team, the Carnegie Mellon team, they are all talking with each other. They are all negotiating roles. They are all sharing information. For now, this one sees the ball, none of the others sees, but they act as if they know where the ball is. It's remarkable to have the multi-robot fill in the lacks of own sensing. And this one here, it's like there. That one, is ready, gets the role from that one through communication, and then acts. Do you understand? But what I'm trying to tell is like this. I know everybody loves the soccer, but I'm so, you need to move so beyond the soccer. You need to move so beyond the soccer. They are communicating, they are making decisions on what the others tell you, not just what you see. And our agents, we all talk about an agent, and I'll explain this. It's very important. They have to understand that now the world is not a single agent, and your sensing is the union, union of all these different agents. So another final example, at CMU, actually in the walls, in the actual corridors of CMU, there are these multiple robots, and I'll show you this beautiful one. So Cobot 2 was coming down the corridor, and it shared with Cobot 4 that it needs to go to Office A. Now, Cobot 4 passes by Office A. It's not its task, it's the other guy's task, but says that the door is closed. And magically, Cobot 2 shares this information, again, communicates. We don't see going through the air the communication. And Cobot 2 learns the door is closed and literally does not go there and replans. Magic again. Can you imagine them all talking with each other, replanning, knowing, sharing? That's what this is. And at Carnegie Mellon, we had 4 of these robots, and I have to tell you one secret. We basically stopped them from going to 4 because we had no clue what they were doing. And we never knew. They were optimizing these plans together. We knew the algorithm, but it was complicated to follow. Where is Cobot 3? Where is Cobot 4? They were all on their own doing these tasks. See what I'm saying? The power of communication also to do this. So the final thing I'll tell you very fast is in addition to other robots, there are humans. And humans, like Tamim said, can help the robots. They cannot pick up objects, and they can ask, please put the actual envelope in my basket. I did not patent a basket on the robot, but I tell you that it was the best thing I did was to invent a basket for the robot. A backpack, a basket. It doesn't have hands, but it can do this. And then we have this problem about what did they do? So the humans, we cannot forget that the humans need to understand what robots are doing. Robots talk this language. They talk like whatever. And then eventually we did this work on verbalizing that particular kind of robot language to language that humans understood. We are talking about 2000 and 17, maybe 16? 17, in which basically this is well before Gen AI, but Gen AI give it logs of sensory data. Can it translate sensory data to actual language? But humans need to know what robots are doing. And then finally also we introduced lights to elucidate humans about what robots are doing. We had like the problem of the robot coming to my office, guiding a visitor. The visitor never knew how far it was from my office. So we did a progress bar from green to blue, from blue to green to approach the robot. And we had all these lights saying you are blocked. And then finally also, I really think that this is very important because Gen AI doesn't do it, nobody does this, which is announcing interesting information. So AI is not only about answering questions. When do we wake up in the morning and AI tells us all these beautiful things that have happened? Our robot would come to my office and say, it was absolutely horrible, it took me a long time to get here. I got it. It took me much longer than usual to get here. And we did a lot of research on transforming the experience of the robot into language reporting on the experience of the robot. And so the robot would, like you were saying, give you data, but what if it would act to the data saying, I found a horrible crater on the way to that point. See what I'm saying? Transforming the actual experience of this robot into this language. Again, communicating with humans, but they are in another world. So the hope is that one day, this is my almost last slide, is that, we have always to acknowledge that one day the world will be millions of agents, robots talking with weather.com, talking with I don't care, with everything, and us humans here in the back looking at all of this. They talk, and Alex Wabel and all of you that work on language, they talk whatever. Definitely not English. They talk sensory data. They talk, what do they do? How does weather.com send like what to my robot? So imagine some language. So hopefully the world will be them talking all with each other. We'll be there and we'll have Gen AI transform what we say to them and back from them to us. And the hope, like Manny mentioned, Marco was mentioning the continuous learning, is that you want these humans and other agents, one way or another, to have another agent improve over time. Improve over time. You need to have this concept that these agents are continuously learning. So anyway, as a summary, I just want us all to think, we talk about agents, and AI agents are not a single agent. Agents can or need to rely on other agents, including humans. And AI agents are not in the business of solving problems. They should be in the business of continuously learning to do them better. So if you kind of see these as a whole, unless we get to this point of having agents continuously learn, it's complicated to think that we have AI. If you go back to origins of AI, be it Turing, be it Dartmouth, be it Alan Newell and Herb Simon, you have to have these be really about, whether we like it or not, being, intelligent. And intelligence is not just perform. Intelligence is perform and learn from the experience and perform better over time. And that's what I wanted to share with you. But don't forget, it's not a single agent. No matter where you are, make them talk with each other. Thank you.
Yeah, thank you very much, Manuela. And now I would like to say a few words also. Maybe you can have the presentation. And before talking about my work and my research in humanoid robotics at Khatib, I would like actually to talk a little bit about the person. Why we have the symposium here about Alex. So a 70 years old machine, which with no sign for slow down, yeah. And of course of Interact. So it has been a pleasure for me to work with Alex in the last 25 years. So I was doing my PhD with Professor Rudi Gadelman, who is with us today here. And everybody in Karlsruhe was talking about Alex Weibel. But as a student, I never met him. We were preparing a large-scale research project on humanoid robotics. And all the professors at KIT, they said, we need Alex Weibel. We need Alex Weibel. In all discussions, in all preparations, yeah, he is on board, but he never show up, actually, in preparation meetings. I think until the rehearsal where he came and he gave really the talk, and I couldn't believe it. I mean, this person never was in the meeting, participated in the meeting, but he gave a fantastic talk. I think it was also a very crucial and important component for this large-scale project on humanoid robotics, what Rudiger coordinated, that you were part of it, not only because of the person, Alex Weibel, but because of the topic. Because of the topic of multimodal interaction, how to combine vision, language, and speech in order to build machines which understand us. So in the 25 years, as I mentioned, I had the pleasure and the privilege to collaborate with him also as a colleague when I became professor at KIT in 2012. We had a lot of debates. And I can tell you something about Alex. Alex keeps always betting for the hardest version of a problem. So he's never actually happy with the solution. If you find a solution, I mean, also his PhD students know them. I had also the pleasure to co-supervise some of them. If you find a solution and they're excited, I am excited about that. They come back, Alex want to have this and this and this more, and again. As we know, and was mentioned several times today, he was working on neural networks for speech, where many people thought this is a dead end, right? He was working 35 years on building bridges between Pittsburgh and Karlsruhe, where also many people thought these bridges will never hold, but we know they did actually for 35 years. And there are so many students actually who came up from Interact, who learned actually and benefited from Interact, and many of them are leaders these days. So thanks a lot, Alex, for all these contributions, not only to your research field, but also to the Karlsruhe students, and for, if I'm allowed to say that, the president is not here, and also for KIT. But let me ask you a question. Where is Alex? Where is Alex here in this picture? The family is not allowed to answer, right? So here? No. Where? Second row? On the left? Okay. This is indeed Alex. This is Alex here. Yeah, this is 1969. Alex as a scientist, 94. Alex as a very important VIP who knows also how to talk to politicians, here with the Prime Minister of Baden-Württemberg demonstrating the KIT lecture translator. Alex with friends and colleagues, but Alex with his many prestigious awards. I think some of the people are here handing over the award to Alex. I'm not sure here, but the most prestigious one is his award for the Technical Field Award, IEEE Technical Field Award in 2023, which is usually given for people who not only really contribute to a field, but shape a field. And I think this is what Alex Weibel did in his career, with his research, and with his team. And Alex is multimodal, you know. I mean, Alex in the space, Alex on land, Alex underwater, yeah. And you will see that he will chair now the panel on exploration, and he will tell us more about these things. But yeah, what I would like to talk a little bit about my research, in particular these parts of research which I have done together with Alex, as I mentioned, the humanoid robotic project in Karlsruhe, which started 2001 to 2012. And these were the goals. This was the vision of this collaborative research project, having a household robot which is able to interact with humans using language, using gesture, to grasp and manipulate objects, to load, upload dishwashers, serve drinks, and to learn from human observation and from experience. Actually, these goals of the project became my research agenda in my career. In particular, the first three topics here, and the last topic was really covered through tight collaboration and very fruitful collaboration with the group of Alex. So where Alex and his team were contributed to the first implementation of a humanoid robot which is able to perform wide variety of tasks in a kitchen environment while interacting with humans in natural language, while detecting humans, persons, gaze direction, gestures, and so on. And in February 3rd, 2008, we were the first group worldwide which was able to demonstrate these tasks. These tasks became a benchmark for the robotic community. Every second robotic group these days have their kitchen in order to demonstrate their capabilities in a kitchen task. And I think with that, the combination of our work on robotics and the strengths of the group of Alex, the strengths of Alex here in natural interaction and communication made that possible. Of course, we continue with this work, and thanks a lot for Rudiger for his support over the long years here for me and for my career, where we developed the series of the AMA humanoid robots. You see here we are at number 7, and we are still working on the same topics, actually, developing robots which are versatile, which are able to provide versatile assistance to humans at homes and nursing homes or retirement homes. You see here an example what the robot can do, and the main difference to many YouTube videos, what you see here, that the complete execution of the task is autonomous. The robot is able to learn from human demonstration. We are able to adapt the actions based on natural language, like wipe faster, what Francisca said, or wipe to the right through gesture. And we are very proud, actually, of this. Of course, as you see, the video is sped up by 10. This is not a limitation of the technology. This is a fact that we only have one of these robots, actually. And if the robot breaks and doesn't work for a few days, then there are 20 PhD students who cannot do anything. Yeah. So just for safety reasons, actually, the speed of the robot is reduced during the execution. But when we work on humanoid robots, we are not only really interested in building a machine for household, we are interested in multi-purpose machines which are able to perform wide variety of tasks similar to a human and at some point even better than a human. So you see another version of our robot which is supporting humans in repair and maintenance tasks. The robot is able to recognize when a human is in need of help based on natural speech, based on force information while jointly collaborating and manipulating large objects, or based on the interpretation of the current situation and the understanding of the underlying task. The underlying task is to repair this conveyor belt, which requires usually 2 people, and if there is only 1 technician, the robot actually should understand that in such situation, my help might be important. Yeah, actually, it's a great day today, and I have been inspired by many people here, not only by Alex and Rudiger, but also by Manuela Veloso, who worked on verbalization of robot experience, as she mentioned. And indeed, Manuela, we didn't tell you about this work, but we continue working in this direction, in particular together with the group of Alex, where we wanted, of course, robots which are able to answer questions, but to answer questions about their own experience. ChatGPT and current AI systems can answer many questions, but having a robot which can answer questions about what Alex, for example, told me yesterday, or told the robot yesterday, or where the red cup was, this is a completely different story. And you see what we are doing here. We are collecting multimodal data, camera images. The sound is not working, right? There is a sound here. we are collecting multimodal data, camera images, how the robot moves, how much force was applied, for example, when grasping a cup, where the cup was placed, and so on. We are training large models. That time, a few years ago, it was end-to-end neural networks, and in combination with pre-trained transformers, so that the robot, based on this multimodal own experience, is able to answer questions. Tell me what you did, please. I moved the multivitamin juice to the countertop. How long did it take to grasp the red cup today in the afternoon? It took me about 1 minute. When did you last see, for example, the red cup? I saw it on December 14th at 15:51. Yeah. This is a very simple example, but I can tell you that this robot generates 350 gigabytes per hour. And we are dreaming and talking all the time about having robots distributed everywhere, which should share experience, should learn from each other, download skills of other robots. This is a very big challenge and very big problem where I don't know actually how it should be addressed at this time. But I would like to stop here. I would like to say thanks again, Alex, for everything. And I would like to conclude here the session and hand over to the next panel. And